Welcome to Lesson 3-5 Residual Plots and Mathematical Models. Our objective for this lesson is to find graphical evidence for how well a given function fits a set of data by plotting and analyzing the residuals. So remember the residuals from Lesson 3-3. Residuals means y minus y hat, okay, or the deviation from a certain regression, okay, may it be a linear regression, an exponential regression, a power regression, a logistic regression. What else? What else did I miss? Okay, nothing more, right? Okay, so for example, let's take this out. A biology class plants one bean each week for 10 weeks. 3 weeks after the last bean is planted, the plants have heights shown in the table and in figure 8-4a. So in case you couldn't see the lower table, so I adjusted the position. 3 weeks after the last bean is planted, the plants have heights shown in the table and in figure 8-4a. So this is the figure. Okay, this is figure 8-4a. Okay, as you can tell, there is a definite upward trend, but it is not absolutely clear whether the best fitting function is curved or straight. So let's look at the data. So 3 weeks old, the length or the height of the bean is now 5 inches. After 4 weeks, we have 4 inches, and after 5 weeks, these are 4 different beans. Okay, so that's for 3 weeks, meaning we began from the last week, because you know this after 3 weeks all the beans have shown growth. Okay, so on week 12 or 12 weeks old, the inches or the height of the beans is 24 inches. Okay, but since for each week since for each week you can notice that the bean heights have scattered data. For example, the oldest is the one planted the first week. So, or after, after 3 weeks after the last bean was planted. So, meaning that the oldest is 12 weeks old, right? So that means that you could see a significant growth on that bean, and you could see that that 12-week-old bean has a height of 24 inches. The 11-week-old bean is 21 inches high, and so on and so forth. So you could see an upward trend for the growth of the beans, right? So in here on this figure, you could see the definite trend. So I'll just clarify. These are the points. Okay. But you can see that the heights are scattered also, so we don't really know which of the functions, the regressions. Should it be like linear regression, or exponential, or power regression? Could it be a curve, or could it be a straight line that best fits the scattered plots? So let us do that on the next slide. So regression shows roughly the same correlation coefficient for linear and exponential functions. So if we are going to run the linear regression on our grapher, we will get this function. Okay, this regression function. So y hat is equal to 2.1351 x minus 4.9636, and that is for the linear function. And notice that if we use the linear function, we have this graph. And notice that some of the points, I mean, it's like a best fit because the points have smaller residuals, right? You can see them, what do you call this, curling into the line. But whereas when we get the exponential model is also pretty impressive because it catches all of the points, as you can see here. So let me make the points clearer. So it's like this here. And let me run this exponential function regression. So if I run the exponential regression, I would get this equation. Okay? And also, my R is 0.9690, which is pretty much similar to the R here with a little bit of consistency. I mean, it's your R here, the correlation coefficient here is higher than here with 0.0015 margin. Okay? So, but they are both like best fitting regression for this data. Okay? The bean heights as referred to the experimental, the number of weeks old versus the height of the beans. So what other options do we need to find in order to segregate, or whether to see which of the two is best fitting? And you can see here that the residuals here are hard to see, meaning that they are really on this point here, they are really like clinging to the curve, which makes them both ideal regression. But take note, so in this case we are going to use the residual plot. Okay, the residual plot are the means to identify the residuals which are hard to see using the regression interpretation by using the correlation coefficient. Okay, because take note that most of them are, I mean, both of them here have residuals which are hard to see. Although you can see that the correlation coefficient are have a disparity of 0.0015 only, which makes the exponential function a little bit better, right? But for the residuals to be seen in a clearer view, we have to do the residual plot. Now to make these plots, enter the regression equation for y hat into your grapher, say in the y equals mu as y1. So L2 minus y1 is of your L1. The expression y1 L1 means the values of the functions in y1 at the, let me use the marker, the values of the function in y1 at the values of x in L1. Okay? So having the residual plot, it's in your grapher actually. So just run this to your grapher and it will show you the residuals. So for the linear function residual, take note that the smaller the residuals are, the better the function regression is. So in this case, when we run the residual plot, we can notice that the residuals here are much easier to see. And in comparison to the exponential function residual on the right, well, the residuals here are much larger or much higher than the residuals on the exponential function residuals. Now, what is the basis here? Look at the residuals on the general. Now, the residuals here, starting with this point, for example, this gives you a big residual, right? And also here and here. Yeah, although some of these clusters through the, some of them are sticking to the line. But in here, you could notice that the residuals are smaller, much smaller compared to the residuals in the linear function. Okay, so the residual plot is a testament that the exponential function regression is the better option in determining which regression is the best fitting for this data, for this scattered data. Okay, so therefore, using the residual plot, you can see much more and clearer the residuals, and testifying that the exponential function residuals on this example and the exponential function regression on this example of a data is the best fitting. Okay, and the better of the two, which includes the linear function regression and the exponential function regression. Okay, so in general, the residual plot interpretation is used. If the residual plot follows a regular pattern, then there is a behavior that is not accounted for by the kind of function chosen. So if there is a regular pattern on the residual plot, okay? In here, do we have a regular pattern? Okay, in here, do we have a regular pattern? Okay, so that's the question. And you can see that the residual patterns here are much higher than in here, right? So if the residual plot has no identifiable pattern, then the regression equation is likely to account for all but random fluctuations in the data. So if there is no identifiable pattern, then the regression equation is to account for all of the regression, okay, for all fluctuations, but except for random fluctuations in the data. So meaning that it could be a linear regression or an exponential regression, right? So that is what is all about the residual plot interpretation. Okay. So that is about chapter 5, the residual plot in mathematical models. Okay. So for the next videos, we're going to solve for some problems involving residual plot interpretations. Okay?